Can anyone confirm that my screen is visible?
Yes.
Thank you so much. Okay, today our major focus is going to be on the aerodynamics analysis on the drone using Ansys Fluent. So, so my talk is briefly going to cover the usage of the tool, how the Fluent can be used for the aerodynamic analysis on the drone. So I'll just I'll take you a deep dive on the fixed wing as well as the quadcopter. So in the fixed wing, I'll just show you a complete workflow and also this allow you to understand the usage and user interface of the Ansys Fluent. And on the quadcopter, I'll just start from I'll show you the mesh. Maybe I'll just take you on how the case and data to be file using case and data file. I'll just show you how the setup need to be done for the quadcopter. So before I just start, as they introduced about me, I had a bachelor's in aeronautical and master's in sports engineering. I just said, oh, just pursue my PhD too. And I am an application engineer. As a passive fact, I love sports, adventure sports, and I'm an animal activist too. So before as we just go to the aerodynamics or computation fluid dynamics, I just like to make sure why simulation is important. So over here, you have multiple goals. Maybe in the aerothon competition, you need to fine tune your drone respect to maybe a acoustics perspective, or want to have a more lift, lesser weight, or want to reduce the drag, want to increase your endurance, or maybe the range of the drone. So that all comes to end of the engineering innovation. But if you now have an idea how you want to implement your innovation, if you just relying only on the product development via experiment, it's always a risk involved and also huge cost and time involved. So how to do a prototype or maybe implement your idea much faster and just catch up, just make sure that your idea is worth to go ahead or not. It's all how the simulations plays a role. So this how this image explains if you're planning to build up a swing in a park with the 3 wooden pieces as well as with the 2 ropes, if just you rely on the CAD model and the experiment, just definitely it's going to be disaster. And the product mark, now what you're expecting to be in the end of your result is always so when you really put a simulation in the product development cycle, so what happens is you can come out with a much better outcome like recycled tire with a one single swing. So your idea can be upgraded and it will definitely take you to the next level just via simulation. So why the simulation important? Before I just go back, I just always have this slide. Let's take Thomas Edison, who's always our major motivator. So 1,000 unsuccessful attempts have been done to find the tungsten as the best material. But now we don't have a time and a huge manpower cost. So now we can do this 1,000 unsuccessful attempts to make your design perfect via CFD tools, large language simulation tools. Okay. So let's just to give you an example, rough example, why simulation or you see our computational fluid dynamics will play a huge role, maybe in any product development. Let's take a simple street light as an example. Okay, so maybe it's already dedicated design, just be there. So just a pole, and I can say there's a lamp on the top of the pole. Simple, right? Do you think we need to do engineering on the street light? Yes, it's required. So there are a lot of parameters and parameter thickness, material height, cross-sectional area, shape also matters a lot. So nowadays, if you see a street light in the seashore is different from the seashore on the hilly region, seashore in the and the street lights in the streets or maybe in the highway. So there are challenges involved, right? Cost, corrosion, wind loads, sustainability, and also transportation. If it's too long, it's very difficult to transport. So all these challenges, all these combinations of parameters we need to be studied before we go to the actual site. So it's nowadays it comes to a customization and also adapt and also designing a product according to the environment. So that's how the drone. So whenever even let's just take a drone as an example. Just we all know the shape of the quadcopter where the 4 propeller is going to be here in the middle of it. There will be a payload. It's well known. If you take a fixed wing drone, anyway, let's choose an aerofoil. We'll have we'll fix it as a wing, and in the mid wing, the fuselage is going to carry a payloads. but still we need to be optimized to the better level, and also we can customize it based on the performance that what we are looking for. So now just getting to an idea of what Ansys roughly. So Ansys is well known, and we are in this market for more than almost half century, I can say. Almost half century we are there, and we have a global presence. So what we do is engineering simulation software, which mimic things. So before you build up a drone, you can mimic the drone and you can make sure what are the aerodynamic force acts on the drone, or you can calculate how it's going to perform in the real world. That can be done using our software. So we are number one in the multi-perspective. We are well proven, and we are extremely high market share. And also we are committed towards acquiring a lot of advanced tools. Just we are not only on the computational fluid dynamics. Ansys has been well known for the multi-physics tools, where we have a huge presence in all the physics, all the perspective of simulation. Can I summarize it as a single-stop solution for complex simulation? So CAD firm, as I mentioned, we are a LHNL partner. So we have 30 plus years experience, and also we have all of our focus is completely on the application side, as I come from. So these are all the Ansys complete portfolios I can subject, but here my focus is going to be on the Fluent in the Fluid bundle. So in the fluid physics, I'm going to use a Fluent solver today to show you how you can model a drone to predict maybe a lift and drag moments on the drone. So what's the challenges in developing a drone? So it's multi-physics, I can say. It's not just single physics involved. Maybe aerodynamics perspective, you can optimize it to have a higher lift and lesser drag. Yes, and FSI is matters, elasticity. You need to make sure you are structurally rigid, structurally reliable. So your pressure loads acts on the drone should not make sure the wing to be failure. So that's the second specificity. And power management, cooling, and also the power management, what you're giving need to be not heavier. You should choose the electronics to be lighter enough. And also it should have a platform and payload integration to carry any particular payload. Maybe like delivering any Amazon delivery, maybe. Or you can also, nowadays drones are delivering the blood from the hospital to the another hospital, delivering human organs. So it should carry human, payloads. And also we need to work on the size and structural limit. If it's not be too heavy and too large, it creates a drag. Too heavy, we need a more lift to lift it. So we should make sure a lighter, so material perspective, and also we should also think about the shape optimization. So we need to remove the material which is not being used, which is not being not necessary. So also weight is a major concern. And flight control, we need to make sure for the flight control, maybe an electronics perspective as well as on the aerodynamics perspective of controlling the complete drone. So there are multiple challenges, and we need to work on the piece by piece. But today, my focus is going to be on the aerodynamics on the side of the drone. Oh, sorry. So yeah, as I said, it's a multi-physics problem. We have a solution across all the physics. Let's comes to maybe a propulsion. Yes, we can do use of CFD for icing. We have a pen cap ice, lightning management. Yes, we have a charge plus electronics and electronics side. We have the ice pack, Maxwell. Also, we have softwares like HFSS for communication side. So I can say whatever you touch or the complete drone, we have a complete simulation solution. Okay. So as I mentioned, it's a multidisciplinary learning. Also, we can come up and do a multidisciplinary research. So it's not just only one department that come and collaborate. For a drone, I can say it's completely multi-physics and multidisciplinary research is being needed, and multidisciplinary approach need to be done. So where the Ansys is coming forward to offer a versatile and diverse solution across all the challenges in the development of drone. So now let's jump into CFD. So to be what's CFD, computational fluid dynamics? which is we have majorly to solve, which has been used CFX and Fluent. Today I'm going to use a Fluent, which is based on finite volume method. So what we do is we should always have a geometry from where we starts up, and they always discretize it into controlled volumes, and we will implement continuity, momentum, energy equations. Okay, all governing equations. Maybe continuity is 1, and we have 3 momentums x, y, z direction, and energy into the partial differentiate in the all discretization and as converting into algebraic, and we solve this problem in our solver numerically. So this is I can say how accurate that we're going to predict. There are multiple factors involved that we work on down the line. So this is the workflow I can say. It's any general computation fluid dynamics. So first we need to have a problem. So let's take a problem statement like now I have a fixed wing drone. I just want to predict the lift and drag on the drone. That's the problem that I am going to solve. And once I predict it, if I didn't get a quiet lift, I just take some design decisions to make the change in the design to get aquatic lift and rest drag. So that is the problem I got to. So next, defining the domain. I should need a geometry. I should understand how much domain I need to have it, because a blockage ratios matters a lot. So once you're done, once the CAD model is there, let's start meshing it. Once a domain is created, and we need to think about what physics and what solver setting I need to do. It's all purely depend on how accurate you need an answer and how fast you need your to be solved. So based on the computational capability and also thinking about how accurate and how fast you need, based on that, you need to do the setup. Once you compute the results, you can examine your results. And once the results is satisfied, you can put the prototype testing and manufacturing. So let's get into so as I said, we have to define a goal. So you should always think of having a goal. So for example, if you want to have a drone, I need to know what are the post-processing I need to do. Maybe a lift, drag. I want to visualize the pressure, static pressure. I want to visualize the velocity on the perspective planes. And based on that, I can understand the flow separation is happening or not. In which angle of attack the flow separation is happening. Okay, so due to flow separation, how much the lift is getting spoiled. So how I can take a decision. And yes, it's all we need to even decide how accurate and how fast we need the results. Accordingly, we need to plan the setup. So next, identification of domain. So domain identifications matters a lot. In our problem statement, it's an external aerodynamics. So we need to create a domain on the top of the drone, right? So what kind of domain I need to choose? Is it can I take a spherical, or maybe I can choose a cuboidal? That thing we need to decide, and how bigger I want. So that domain size will also. So where are the blockage ratio come to? So generally, the blockage ratio must be somewhere between 3 to 5%. So that decides the size of the domain. So there are multiple of these factors. I mean, domain, size, and boundary conditions. So can I go to far field? Is it okay to go with inlet velocity and pressure outlet? So these boundary conditions will also take it to be decided before we jump into the problem. Accordingly, domain need to be created. Next, we need to create the domains. So once we've been planned to create a domain, then creating a domain out of it is another things to be done. So in Ansys, we have give you end-to-end workflow from geometry. Once the geometry is ready, we have a CAD model. From domain creation to post-processing, we have a tool. So for geometry cleanup, domain creation, we have a specific tool, space climb. I'll just show you during my demonstration. You can use a space climb to create a domain out of it, and where the domain will act as the fluid flow over the drone, where we have protection and post-processing that we're going to do. And next, we need to for the meshing. So how much mesh, how much cells or nodes is required? It's completely purely depends on the grid independence study. We need to do a grid independence study. Maybe you're down, or maybe during first prof, during the best practice, I'll just give you a much more clarity on the grid dependency, and that's how much that I need to mesh. For example, let's take this car. Maybe if I'm looking for a heat transfer on this particular region, I need to do a fine mesh on that. So we have to decide where the fine mesh and post mesh need to be. rather than choosing a global sizing, I always recommend to go you with the local sizing. So it's always to be far before we start the mesh, we should have an idea where I need to have a fine mesh, where I need to have a coarse mesh. That will help us to save a lot of computational efforts and also the requirement on the computational machines. So with our efficient decisions, we can save a lot of computational efforts, definitely during the meshing, and also we can accurately predict the physics on the any problem. The fifth step is always a solver. We should understand what material property. Yeah, for here the material property is simple here. Yes, but there is a certain constraint you need to look for. So where altitude drone is going to fly? You're going to simulate. You're going to simulate a cruise. Okay, what's the altitude is going to be? So accordingly, the material property need to be there. Accordingly, the pressure, density and viscosity of the air need to be inserted. And second, we need to also plan what turbulence model you need to use. Generally, yes, SSTK omega is a jumping default. It's good to go with, but I also need to think about, is there room for other turbulence model? If it's too separation, we are looking for flow separation. Yeah, in that sense, what turbulence model is the best? That we need to be make sure before we are going to the setup. So this very important thing that we need to look on the turbulence model, and also the boundary conditions and all the setup, maybe inlet, or is it you're planning of going to with a velocity inlet or pressure outlet, or maybe a mass flow inlet. What kinds of inputs that you're going to give to the solver to solve the problem, and also the solver controls. What are the things you're going to monitor? Lift, drag, or pressure on any particular plane, or on any wall, maybe all the velocity on the plane, that we need to decide, and also the convergence monitoring. So are you planning to go to a 10 to the power -3 or -6? That decision, it's extremely needed to set up the solver. That communication to the solver will help you to make sure your result is accurate and also converged. And we should always look for the convergence. Yes, true. But doesn't mean the solution is converged, it's accurate. So that can mean we need to check on the verification and validation. And also we should think of what are the assumptions that we need. Is it mesh resolution is enough? The grid independency is being converged or not? All this computed solution is also been a matter. And also we need to look for the balance, maybe a mass flux balance is attained or not. So these things need to be conducted and controlled during our convergence of the solution. Once the solution is converged, next we need to examine our results. Maybe we can look for any contour visualization to understand the separation, to understand the shock, shear layer, to understand the boundary layer, to understand the flow separation, vorticity, much and more and more. And also you can look on the numerical results like quantitative results like force, moment, on the drone, and what is the any surface and volume integrals of the quantitative which is being you're looking for. So all this maybe you can also look for the lift distribution on the wing for your requirement. You can understand. So accordingly, you can change the wing designs also. You can change it as maybe the wings have been aerodynamic twist or geometric twist. According to the lift distribution, you can change the twist on the wing to make sure have aquatic lift distribution. So also they'll be look for on a wing. They also look for elliptical lift distribution. So in that having a lift distribution shall make sure you are having an adequate elliptical wing distribution, lift distribution on the wing or not. So you can also automate this process. So you're examining the results. Your result is not maybe it's not adequate. You are not satisfied. You have to go back to the geometry and to change the geometry and need to come back again. You have to follow the process. You can also automatize that using Design Explorer or OptiSlang, where the CAD model is optimized and changed according to the acoustic result that you're looking for. These kinds of automation is also possible in our Ansys solutions. So as I mentioned, it's completely end-to-end workflow. So once you define a goal, the geometry can be done in a space climb, meshing, setup, solve, all, and post-processing, all can be done in the Fluent alone. So the meshing is also done in Fluent Meshing. is a wonderful meshing software. It's been easy for the I can say it's extremely easy for a beginners and also for the traditional user. It's completely flexible and robust to being used. And why? I mean, Ansys also offer you a GPU. So not to rely on the HPC high performance in computing, you can also use a GPU to run your problem without compromising your results. And now we have rotating wheel, full wheel turbo machinery, mixing application, which also allow you to do MRF, which means quadcopter can be solved, and also external aerodynamics GPU is something highly recommended. As you see, just two GPUs 16 times faster than 128 cores. It's faster and also efficient, and plus, without compromising your accuracy, you can get the results. And we also have a Fluent Aero workshop, workspace, which is a tailored Fluent user interface. I recommend all viewers, please look into a Fluent Aero, which will help you to solve any aerodynamics, any flight aerodynamics problem from subsonic to hypersonic level and across altitude level. So re-entry vehicle, maybe a drones or airplanes, all this can be solved. This is something extremely useful for definitely for a drone design, actually fixed wing. Please, I recommend all of them to just please go and check Fluent Aero workspace. A lot of tutorials have been also available. Please, I just recommend you to go across. And apart from that, Fluent Meshing, as I mentioned, why Fluent Meshing? Because we have mosaic technology, which is automatic combination of distributed meshing with polyhedral elements, which is fast and accurate. This will make you lesser sizing. Compared with the conventional tetrahedral, polyhexal core has a 46% of size reduction. Okay, it's all approximately 50%, I can say. This will help you to solve your problem quickly and with lesser computational demand. So that's the power of Fluent Meshing, I can say. And also it's easy to use and faster also. So we have two kinds of workflow. Yeah, one is watertight geometry. So it starts from the importing the geometry. You need to import it. Once you import, we need to generate a surface mesh. Once surface mesh is done, we can go to the regional extract. Once the region which will have a fluid volume alone. So you can do a volume mesh and just set up and solve and do the post process. It's completely single window. So once you have a CAD model, just put your CAD model into a Fluent, just have a geometry, have a surface mesh, extract your region, do a volume mesh, set up, and do the post processing. And also we have a fault tolerance method where some geometries where it's difficult for us to make it watertight, completely clean, where this helps you to create an objects and also to identify the region where I need to be stitchings to be done. And just once you fix the leakages, you can also do a sizing control and wrap it, and you can do a volume mesh and just run it, take it to the setup and solve it. So even it's a complex geometry, it's with a lot of openings and stretches, even though you can do a meshing, and also simple watertight geometry can also be done. So in your case, it's completely drone. It's very simply we can make it as a watertight. So my demonstration is going to be strict on the watertight geometry. So wow, simulation is driving engineering to help the drone development is maybe if you want to reduce the development time, you're starting it, there will be a time bounded. Yes, you can reduce it, and also cost where it will allow you to do a less prototype and also optimal your weight, optimum your performance and aerodynamics, noise reduction, structural integrity, reducing your weight, system and payload release, and how the once a payload is released, is it released safely? Is it landed safely? All this can be studied. Different scenarios can be simulated, and you can understand that your drone is operated in the safe and wise condition, and expected performance being get it out or not. So that's the power of simulation in the driving and engineering in the drone development. Okay, so if you have any questions now, you can ask me, or else I just maybe I'll just take you through some demonstration next. Any questions? Hello, am I audible? Okay, I assume there is no question. Okay, let me check the chat box also. Okay, so, okay, just give me a second. I'm just loading the file. Okay, so this is the drone that I'm going to do a demonstration. So what I've done is I just opened the space client. Okay, just type space client and just open the space client window and just go to file and open, and you can just open the CAD model that you have to want to do a simulation. Just open this fixed paying CAD drone. So what I'm going to do is first thing, as I mentioned, I need to define my goal. So my goal over here is I just plan modeled with one particular aerofoil with a drone. Also, I have a wing or to reduce the vertices. So I just want to make sure I know what's the weight of this drone is going to be. So aquatically, I'm looking for some lift out of it. So I just make sure that I'd add a respective lift, and I also want to measure the drag. So accordingly, I can also plan the propulsion system of this drone for this particular drone. So now I just first thing, once a goal is defined, I need to plan a domain. So this is how the interface is going to be. So you can do some basics CAD modeling also. So this is a sketch model where you can have a line, circle, different shapes. You can do 2D shape from here. You can go to design and use a pull or pull to make it as extrude. And also you can move the CAD model, fill it, and also combine. This is something can sound similar to the all CAD software. And you can also do a displays. You can do some assemblies. You can measure it, press it, repair it, and repair it just helps you to do a cleaning up the CAD model. And also you can do a prepare. So here I'm just going to the prepare to prepare my CAD model where I just want to make a domain out of it. So I'm just selecting my complete CAD model now. So now complete CAD model is selected. And also I can have some controls on my keyboard also. If I press H, it comes to isometric view. Okay, so I just been pressed. So I'm just going to make an extrude now. So I'm just, once I press the extrude, you can see a cupoidal box being displayed. So now with this, you can see a different in the property window. I can make a box. I can also make a cylinder. So you can see the cylinder, and also I can make a sphere. So based on my requirement, I can create any shape, and also you can do a custom shape. But at present, I just want a box. But also, I don't need a symmetrical dimension. I want unsymmetric. So once I make the unsymmetric, now in all direction, I can feed the dimension. So what I'm going to choose is, since it's a demonstration, I'm not going to have a bigger domain. So that will cost me more time and time in the demonstration. So I'm just going to take a decent domain size. But I recommend you to calculate your blockage ratio and to maintain somewhere between 3 to 5. Okay. So this is 6 in the front, and also, oh sorry, I'm just hitting 6 and using my tab. I'm moving to in the rear. I'm just giving 20, and OER 6, OER 6, all directions 6, front, half, down, and the side. Okay, and only on the rear I made 20. So once you are done, once you feed all your dimensions, you can just tick that to give you it's complete. Once you're done, I'm just hitting the escape twice, and again I'm pressing the H for the isometric. So this is how to be done. So you can just sign it now. This UAV is a CAD model. This model which has been taken. This is my enclosure. So once it's done, I don't need this model, right? So I'm just unchecking it because my enclosure will have a pattern of this particular drone. So you can see even if I uncheck, you can see the drone inside, right? So also I didn't need it for my physics, so I'm just doing suppress for physics. So I'm suppressing it for the physics. It's not being needed for. So now I'm just clicking on all the four sides, and I'm just pressing it. I want to give a name selection. This will help me to give a boundary condition on the prospective name. Maybe I can give a for field, or maybe you can also give symmetry, because I'm going to give a symmetry boundary condition on this. So based on your convenience, you can give, this is an outlet. So I'm just going to give an outlet. This outlet is going to act as a pressure outlet. This is going to act as a inlet, velocity inlet. And now I need to name the UAV model. So what I'm going to do is I'm just checking the file for field, and I'm going to hide this for a moment. So I'm just dragging my mouse over the CAD model. So it's completely selected. So you can see it's completely selected. And I'm just going to give a create NS and UAV. So it's selected now, right? So I'm just clicking somewhere on the screen and just hit show all. It will show all. So you can see UAV is there, inlet is there, outlet is there, and also profit is also there. So things are fine. Now you can go to file and you can hit save and save this. Okay. So it's depends. I mean, what do you save? You like to save? Just save this. So once it's done, and what I'm going to do is I'm just going to launch my Fluent. So I just going to use a meshing. So I'm just hitting my meshing in my Fluent launcher, and it's double precision, which will make me accurate. But it's always recommend to go with double precision. And also, I'm just taking a processor. So I based on my HPC license as well as based on my hardware, I need to choose my processor. My hardware is 36 core. So I'm just choosing this 24. So this is something efficient number of cores, which will help me to scale up my solution. So I'm just taking the process. Generally, in each solver, early inbuilt is 4 core. You can also use 4 core. This I want to be a little fast. That's why I'm just taking 24. Okay, I'm just hitting start now. Okay, now my meshing window is loaded. So what I can do, so going to select the workflow. So I can go with watertight as well as fault tolerance. So my choice is going to be watertight because our this clean and watertight geometry. It's very simple geometry. So now on to fault tolerance. And yes, now the latest version 2D meshing is also supported by Fluent. Fluent. Meshing, you can just choose based on your requirement. I'm going to choose my watertight geometry. And now I'm just going to click import, and I'm going to import the geometry. So I have saved my fixed wing model of enclosure. I'm just loading that. So in a console, you can see as it's loaded, all the information is being printed in the console. So I'm just making a bit intelligent to see. I'm just using insert plane. So now I can see what's my just again my drone inside. So my drone is inside, and also the domain is crossed. So this is how it looks. So let's now I just go into generative meshing. So this is completely step by step. The solver will ask you multiple questions, so you can keep answering it. Like it will lead you to a recursive step by step. Start from import geometry. Next, it starts to add the local sizing, and it goes till the volume mesh, which is the end of the meshing. So first thing is on add local sizing. So this will allow you to do a fine mesh on the respective volume or maybe on the respective surface. There are multiple methods for there. Maybe I'll just, today I'm just going to do a no to local sizing, but still I just want to take a moment to explain how the local sizing works. You can do a face size, you can do a body sizing, and also you can do a body of influence. You can create one dummy CAD model internally, and you can create you can build a fine mesh on in a particular volume, and also to have it on the surface. You can use also face of influence and curvature and proximity also can be targeted and mesh. And also, if I can select a particular, maybe in a face mesh now, if once I selected the UAV, you can see the UAV has been selected, and I can give a respective values to mesh this particular UAV body up completely. So you can also name the objects, which is need to be have a local sizing mesh. Since it's a demo, I'm not going to do this, and because it will cost me a lot of computational timing and effort. So I'll just mark it 0. No, but I recommend you to do add local sizing for your problem. So I'm just going to update it. And now you can also see we are going to move to the second, third step, which is a surface mesh. We have a control on how much minimum their mesh size need to be. And maybe I just give you 10, and also I just going to give you 500. So this is my minimum maximum. You can also have a control on growth. We can also understand curvature angle to ask you reduce the curvature on the curvature the fine mesh is going to be. And also, if you want the meshes to be generated more on the face or edge, you can also have a control over there. And yes, you have some advanced options too. But generally, you can play more with the minimum and maximum sizing. And also, they've had you to scope your proximity. I just changed the minimum and maximum sizing now at present. But I didn't keep all other parameters at default. I'm just hitting my surface mesh. Yeah, it takes at least 2 to 3 minutes roughly. Okay, you can see the surface message being generated successfully. Now let's move to the second, next step, which is describing the geometry. And now I need to describe my geometry now. During my describing geometry, so there it's looking for what geometry type it is. So it's actually a fluid region alone. I'm not I have only the air fluid region. I hope you remember in the space climb, I just uncheck. I subtract the complete UAV model. So we have only the fluid domain. So I just selected this and I kept other as in a default, but you can just play across when it's been required to describe your geometry. And I'm just going to next, and you can see a for fail, pressure, outlet, UAV. So and I need to be, I want this to be symmetry, but I just keep it symmetry maybe, or else I can even change it in my solver. So maybe I'll just change it in my solver. So I'll just, to give you a better example, flexibility, even you can change it here, your boundary type, or maybe on the solver also. I'm just updating my boundaries. And if you have a 2 fluid, but we are having only 1 fluid region, so which is complete domain, which also has a UAV outer area. And second fluid, which has been showing only the unmanned vehicles surface. It's as an internal volume also, but it's not required for us. So I'm just marking this as a test zone, and I want only the enclosure. So I'm just going to update the region. And over here, boundary layer, there are multiple techniques is there. So you can create a choose a type based on the technique you like to do it. You can make a smooth transition, uniform means it's across the fluid surface. It will give you a uniform boundary layer. So why we need is this will allow you to capture the fluid physics near to the wall, and also it does allow you to understand how the boundary layers is there, now the separation is going is there in the surface. So generally for external aerodynamics, we go with the loss ratio technique because it does will allow you to have much control on your first height, which means Y plus. You can use your first height need to using your first height you can have a control the Y plus. So now I'm just assuming it to be a 1. And generally, in external aerodynamics, the recommendation is must be have somewhere around 10 to 20 layers of mesh. I'm just choosing 10, and using your required Y plus, you can have a control over your first height. I'm just choose to 1, and I'm hitting a boundary layer. Yeah. Now one more thing, you can also need to choose your label where you want it, or you can also have a growth on complete wall zone as per your requirement. I just wanted the development only on the UAV. So I'm just selecting the UAV by selecting the labels. They already have them named. So I want the mountain need to be developed only on the walls of the unmanned aerial vehicle. So once that is done, my final meshing is I need to go to change to polyhexacore. So which is highly efficient. During my presentation, I told the polyhexacore is comparatively have a lesser number of cells. Regular tetrahedral, and also you have a flexibility to develop hexacore or a polyhedra. So, but I just go with the polyhexacore, which is recommended even for your almost all room external aerodynamics problem. It takes a couple of minutes, maybe. Oh, it's faster. Okay, it's done. So you can have a. Maybe I'll just choose another. So you can see a message generated, and also you can see boundary layers is being generated to capture the boundary layer mesh to capture the physics near to the wall, and also in a graph. So it has a fine mesh near to it. It's a step. The mesh has been created. You can also, if you're interested to understand the wake behind the this unmanned aerial vehicle, you can also have a fine mesh across the complete UAV using body of influence method, or also you can do a lot of local sizing method. You can also keep a wrap around it. So we have a wrapped additional options which is available in the add local sizing. You can add that, and you can have a fine mesh completely surrounded across the UAV. So this is how the mesh need to be done. So maybe I can, if you have any questions, I can address till the meshing, or maybe if you have any questions on the space climb side, I'm happy to take it. You can also feel free to drop some questions in the chat also. So any questions? Anybody? Okay. Okay, I assume there's no question. So maybe I just take it the solver side. Yeah, please.
Hello. Yes. Sir, can we do this in Workbench using Fluent, or we have to launch separately only?
Oh, okay. I used Fluent in a standalone mode. You can also do it using Workbench also. Maybe I'll just show you how to do that.
Okay, sir.
So you can go to a search, you can type Workbench 2025. I'm just launching that. Okay, so you can use Fluid Flow, right? If you use this, it starts from geometry and the meshing will be taken to Fluent Meshing. Okay, and also you can use the in a component system Fluent with Fluent Meshing. This will start from the Fluent. Okay, so any questions? I got it. You can also do it from the workbench, but make sure you are taking Fluent Meshing. As per your, if you want to start from the geometry, you have to go take it from the fluid flow. If you want to start from the Fluent Meshing, you have to take from the component system. Okay.
Okay, sir. Okay, sir.
Thank you. So I have to answer. So any questions? Okay. Fine. So I had now I can also switch to solution. I can click switch to solution. This will make me to the Fluent solver. I'm just hitting switch to solution. I'm just hitting the solver. Just taking me to the solver. I mean, user interface will be up to the making it to the solver user interface from the meshing user interface. Takes a minute. Okay, it's loaded. Now I can just display the V, and also I can display it as a meshes, so I can save it. And also I'm just going to give a check. This will show you if they have any bad mesh or anything it's not loaded properly. And also I'm just clicking the quality is safe, everything is good for the meshing side. So now I just want to explain you how to set up your problem in the solve, which is the important and master part of the CFD. So once I've displayed it adequately, I just did a check and report quality. And if you want to change anything on units, you can go to the units and change the units. Maybe if I want to, for example, if you're doing quadcopter, you want to give angular RPM, but here the SI unit of angular velocity written per second, you can change it to RPM, revolution per minute. So as per your requirement, you can change the units if there's anything to be changed. And next, we have to look for the solver type. It's general best practice is for subsonic, it's pressure-based is more than enough. So I believe most of your problem is on the subsonic. So definitely you can go with the pressure-based. When it's highly compressible flow, we recommend density-based, maybe high-speed aerodynamics. And also velocity, maybe formation, maybe in substitute is something label and to be given for your kinds of problem. And I can also change if steady and transient. It depends on your problem to problem, what you're going to measure. You can change steady with respect to steady, or maybe change with respect to time, so that you have to go with the transient. And you can check it and check the gravity also. If you want, you can also add the gravity in your problem. Since I'm using hair, and here the gravity is definitely it's going to be very less on our fluid. So I'm not going with the gravity, and it's all I just keep it default. So I can also go from top to down approach and also left to right approach. Both are almost same. So it will be separated into setup, solution, result. In the top domain, physics, yeah, user define function is not required now for you. Solutions and results. So I can just start using the top to down or left to right based on your convenience. now I just jumping into the physics once all the fundamentals have been checked. So these are the general. I just click general. Sorry. So now in the physics, I want to set my operation conditions. So I'm just checking my operational conditions. So the operational condition is 101325, which has been sea level. So based on your requirement, you can also change the operating pressure condition. If you want to study in 1,000 meters from the sea level, please make sure you're giving a right operating condition. And second, next I need to check the model. So I'm just going to click the discuss model. Yes, then here I have a room to select my turbulence, what kinds of turbulence model I need to be used for it. So I want to use a K omega SST. So just been a default, but even you want to go to Chico, yes, you can change it, or you want to use epsilon, yes, you have a room to do that, and you can change if it's in a transition phase, your flow, you can also change it accordingly based on your problem and requirement. But I'm not going to change anything, just keeping it default, because I'm happy with SST omega for this problem. So I'm just changing it, and also you can change the other parameters over here based on your requirement and needed. Once this is done, I have to go to the material. So I can click and create the material. The default material is air. So since air is going to flow over this UAV, there's nothing to change, but be cautious on the density. Just both or this two values, viscosity is in a sea level. So I'm not going to change that. I'm going to give a sea level condition only. So if you want, you can also go to Fluent database and pick up the fluid that you want, and also you can just create your own fluid also by just clicking up, changing the name and giving the values. Okay, so here also there is no change, because the air is a default that I am looking for. And in the cell condition, the enclosure, I need to make sure it's an air bounded enclosure. So since I'm just only one fluid, so it's a air is there, and also I don't need a moving frame. It's all need to be fixed, and there is nothing to be changed across. These also need to be default as enough. So I'm just applying and just closing this. And next, what I'm going to look for are boundaries. So it's a far field, which means that all four sides of this domain has been changed, but I'd like to keep this as a symmetry, which will give a split condition where the boundary layers will not develop on this walls of this all four sides of this domain. And also next boundary condition, I need to look for the inlet, which is a velocity inlet. So I can just click edit and feed a value. So I'm looking for what happens to this drone when it flies at 25 meters per second. So I'm just feeding it 25 meters per second. But one more thing, you can also change the angle of attack. So you can change the angle of by just giving a magnitude and direction. You can change the angles. It's required. But now I'm just looking for a zero angle of attack. So I'm not going to work on the direction. You can also change the component normal direction based on your. So you can change the magnitude and direction and component. As a component, also you can feed it. But now I'm just looking for only a normal to boundary. I'm not looking for any angle of attack. I want zero angle of attack, and also make sure can also have a room to change the intensity and viscosity ratios, but I'm just keeping it default. And the second thing, I'll just look the pressure outlet, which is need to be fed as a gauge pressure. The atmospheric gauge pressure is 0. So I'm just giving atmospheric gauge pressure on this as 0. So you have to make sure you're giving a right gauge pressure for your problem. And the UAV has been considered as an upward. So things have been set up now. So there is nothing to be worried about on the physics side once the boundary is done. Next, I can move to the solution. So in the solution, first thing what I need to do is I need to check up the method. So it's a default in coupled, but you can also change it to simple or cyclic. Yeah, for this problem, couple is good fit. So I'm not going to change. If you want, you can also change something on the position control. You can change the momentum or pressure, pseudos, relaxation factors as per your requirement. Okay, that's our thing. So while defining the problem, I just told you all that I want to look for what's the lift and drag axis on this UAV. So I'm just going to define it. I want a force report during each iteration. So first thing I'm looking for is a drag. So I'm just clicking the drag and need a drag force. So if you want, you can also keep coefficient. I just click the UAV. The drag force acts on the X direction. So I just make sure it's activated on the X. So this is going to be my drag force. Sorry. So done. The next, what I'm going to look for is the lift. So I'm just going to the force report and I'm just creating a lift. Force. I change it to lift force, which is to be in a Y direction, and also make sure it's in a Y direction. So click it. Okay. Even you can also look for any maybe a surface report area weighted pressure on the average pressures on the any particular wall or a plane. So we recommend, and also you can for a moment if required, or maybe you can also create any respective force act on any part of your UAV that's purely based on your requirement. Okay. So once it's all done, I'm just going to do my installation, just being a hybrid. Yes, hybrid is much better. I mean, far better for this. So I'm just initializing my problem now. Okay. And I can feed my iteration, how much iteration I want. Okay, I'm just going to hit calculation. And also, one more thing you can look for is this convergence. So, yeah, from here, I mean, you can also activate it from here, check this from here, this residuals. This, I'm just keeping default. If you want, you can also change this to e to the power of -6, where your accuracy may be improving. But since it's a demonstration, I'm not just going to play much on that. So I just keep that default, but also make sure you have the right residuals for your problem. So I'm just making it 100. Hit, so I can see my scale residuals continuity, X, Y, Z momentum. And yes, we need a K and omega excess unknown equations to solve the unknowns, except two equations to solve all our unknowns. And you can see the drag force as well as the lift force with respect to the iterations. You can see the residuals are converging. You can monitor here, and you can also see a console the iterations have been running faster. You can see the solution is converged. Okay, so if I didn't tighten my convergence criteria, so it's converged faster. But I recommend you to tighten your convergence criteria. So the mesh level, I didn't have a extremely fine mesh, or I mean not extreme and required level of fine mesh number of fine meshes. So you can see the it's almost constant convergence is in attained, and also you can see the residuals have been converging. So this is something good to know. So now let's go to the post-processing. I mean, I want to do post-processing. But before I just jump into post-processing, I like to take some questions. Maybe but that's the right time now. I can take some questions. If you have any questions, please feel free. I can, if you want me to show something there, please you can ask me some questions. Feel free. Any questions? Or I'm just a bit of a process. Yeah, let me check the chat box. Okay, there's no question. Okay, fine. I'll just assume there is no question, and I'll just go to the first processing. So in the results, I can look for. I'm just not looking for a contour first. So I just search the technical contour. So I want to understand how the UAV static pressure on the UAV. Just I selected my UAV and just click event display. The moment I done, you can see the event. You can see that it's completely displayed on the screen. So I recommend you to just, you can see that it's a high pressure in the bottom and also the low pressure on the top. It just lead to a lift. And also you can see one more thing, stagnating pressure on the wing and the nose of the drone. This lead to a huge drag, this pressure difference. So compared to the tail region, there is a huge stagnating pressure on the nose as well as on the wing. This lead to a drag. Okay, maybe and now I can also create a plane. I can change the axis, maybe to XY. You can see it's on XY. And I'm going to name this as a center, plane center, create it. And also I can see what's happening on that particular plane also. Okay, cool. Now I just like to see what's happened on the cross section of the wing. So I'm just creating another plane, maybe on the axis. And I just name it as a wing. I'm just creating another plane. Oh, sorry, the wrong direction. Just creating a plane in this direction. Into one. Just make sure. Okay, it's there. Great. I just want to see the static pressure. Now you can see the static pressure on the wing also. You can see bottom has high pressure and this has a low pressure region. So that's why the lift is generated. Also, you can see a stagnating pressure on the leading edge comparing to the trailing edge. The pressure is high on the leading edge, which is lead to huge drag. Drag on the wheel. So this is done now. And also now I can look for the velocity. Maybe I'll just uncheck the UAV because velocity on the valve is 0, right? So I just can see in a cross-section area how the velocity field is. So you can see a higher velocity lead to a lower pressure. So you can see high velocity region. And also you can see a boundary layer, a thinner boundary layer. And once the distance keep increasing, boundary layer thickness is also increased. You can see a boundary layer over there. And also on the center. So this is the velocity profile on the drone center. You can see high velocity lead to low pressure, lead to low pressure, and here compared. So this is as a decent velocity, and here the velocity is high. So here it gives a low pressure. So the lift is being generated. So that's how we can look into it, and also we can go to report. Maybe I'll just go for the bottom of round, and I can just go to the forces. And I want to measure force on the UAV. First, I want to measure it on the X direction. So let me show you what's on the X direction. So X direction is going to be a drag force. I'm just asking to print. So it's printed in the console. It's 39 Newton. So I can also get a pressure force and viscous force separately. So it's almost both are almost same. So I can understand the drag force is somewhere around 39.4 Newton. Okay. And all now I want to look for a lift, which is in the y direction. So I'm just marking it 0, and I'm marking it 1, and I'm just going to print it. Okay. You can see my lift is somewhere around 700 Newton, right? So 712 Newton just for the graph. So that's how you can print it. Okay. So I like to inform you one thing over here. So here I done it for maybe I'll just show you it in the contour graphics. Because I want the pressure. So this study have been done in the 0 angle of attack. Now just imagine you are doing it for 5-degree angle of attack. So the angle of attack is angle between the free stream and the chord. Okay, but solver doesn't know where is chord, right? So the measure of all the forces is taken respective to the coordinate axis. So you have to make sure the conversion between the normal force and the lift is done, axial force and the drag is done. Okay, so solver will always give you a force, I mean, in the normal direction and axial direction. We have to convert the normal force into lift force, axial force into drag force when it comes to a different angle of attack. In angle 0, the axial force as well as the normal force falls on the same. I mean, axial force is equal to drag force and normal force is equal to lift force, but it's not evident in other angle of attacks. So make sure when you're doing it in other angle of attacks, the make sure you're converting the axial force into drag force and normal force into lift force. So that need to be little caution. You have to be caution on that side of the post processing. And also you can look for a vectors where maybe this will help you to understand the separation, flow separation, where the flows, you can see the capturing boundaries and being captured. Maybe I can just change it to 0.5. So this will give you some better, and you can see a boundary layer development on the surface. This will help you to understand the separation, flow separations. So you can see flow separations is being happened. The flow is getting reversed, right? You can see the flow is getting reversed. Just move this. You can see the flow is getting reversed. So slightly the separation is being observed in the rear side of your drone. Okay. So you can think about how to control that. Is it leading you to a huge pressure drag? So this will help you to understand the separation point. So is there any further like to have any questions? Please feel free to ask me on the post processing side. Okay.
Sir, how to proceed if our model has propellers in it, sir, especially in the mesh part?
Okay, fine. So I'll explain. I mean, you are asking for a multi-rotor or maybe in the single fixed wing
Sir,
with propeller.
multi-rotor, sir.
Okay, multi-rotor, I will address that. Maybe the next demonstration, I'll show you multi-rotor.
Okay, sir.
Sure. And even if you want, you can also do analysis with the single, I mean, with the fixed wing will also as a propeller. With propeller also, you can understand how the propeller interaction is there. But what I've done is without propeller. Maybe I'll show you one case which has a propeller. Just allow me a second. I'll just load that case.
Yes, sir.
Sure.
Excuse me, sir.
Sorry.
Hello.
Yes. Tell me.
Actually, is there any way to speed up the simulation? Actually, we are trying to do transient analysis of multi-rotor, and it is taking much time. So it is like, is there any way to offload all the load on GPU or something like
Yeah,
that?
second demonstration, I'll do it in a multi-rotor using GPU. I will also share some technical contents on that. Definitely, I'll cover that.
Okay, sir. Okay. Thank you.
Okay, thank you. Yeah. Just a minute, I'm just loading a case to show you how to do for a propeller, maybe the fixed wing also. Just allow me 1 second, or just a couple of minutes. I'll just show you a geometry and I'll explain you roughly, I'll give you a rough idea how we can proceed.
Sir, sorry, but you are muted.
Oh, I'm sorry. I'll come again. I'm sorry. Thanks for that. Okay. So this is the problem I just want to share with you all. So if you want to solve unmanned aerial vehicle with propeller, it's also possible. So I'll just show you an example. So I had a unmanned aerial vehicle which has a airframe and also the propeller. The first thing what I have to do is I need to make it separate. So propeller is separate. Separately, the propeller is unchecked. So this is a propeller part, and this is a airframe of that UAV. So I also need to make an enclosure separately. I just made an enclosure for the propeller, and also I need an enclosure for the complete drone and domain. I mean, as I just shown a demo. So only one thing is going to differ from what I've done. So what I have to do extra over here is I need to feed a solver what is the RPM of this rotor. Okay, so you have to consider this as an MRF zone. So there will be two fluid region. One fluid region is going to be an enclosure, and this propeller enclosure is going to be MRF zone. Okay, multi-reference frame. So this will help you to feed what is the RPM of the propeller. Okay, only that information that you need to feed in the solver. Other than that, all the setup and what I've done, this is almost same. Okay, you can use the same workflow to solve your problem when it comes to propeller. So if you have any questions now, if you don't have questions, I can just move to the next demonstration, which is on the quadcopter.
Sir, the main reason for this increased computational time is in mesh, sir, or setup. It is most probably in mesh because mesh, I think so. So how to rectify that?
Okay, fine. Yes, there are there are multiple things that we need to do, ma'am. First thing, we have to do a local sizing. Please don't do a global sizing. What I'd shown a demonstration of global sizing, but I always recommend to do a local sizing. So what that local sizing means, we have to do a fine mesh wherever it required. Please don't do a complete domain as a fine mesh. So do a fine mesh wherever it required, and other region, please make it coarse where it's not required. If you want to observe a wake, have a fine mesh behind the drone. If you doesn't want to look for a wake, you only want to understand what's the physics around the drone, just make sure you have a fine mesh only around the drone on the surface of the drone. That's the first thing we have to do. So avoid the global sizing, having a fine mesh complete domain. That's the first thing I'll recommend. Second thing is please use Fluent Meshing, because in Fluent Meshing you have you can use a polyhexacore. This will drastically reduce the computational timing and computational machine which is required. Okay. So, and the next smart way of doing is you can use GPU. So you can please use GPU and make sure you have a right GPU with you. So, I mean, you must have an idea. There are multiple recommendations are there. So please make sure that respective supporting GPU card that you add in your hardware, and please use a GPU to enhance your solver as per the, it will scale up your problem easily. So that's the thing. So first thing is make sure you're doing a right mesh. And second thing is on the polyhexacore core, which is generally, and also use Pew technology, which has been also help you to make scalability on the scalability side. And yeah, as you mentioned, ma'am, turbulence model is also on a making efforts. But I can say SST Omega is somewhat best for external aerodynamics. Yes, you can rely much on that. So other than that, if you're going for maybe some other turbulence model, it will definitely have an effort on the computational timing also.
Okay, thank you, sir.
Okay. So now, any further discussion or questions? Feel free. We can have I can have some more questions before I go to the next. Let me check the chat box also. Okay. Oh, sorry, I was on mute for some time. Then how to analyze a multirotor? I'll just go there, explain how to do a multirotor study also. Okay. Is there any questions? If there is no question, we can move to the maybe next part of our demonstration. Okay, I assume there is no question. Okay, just allow me a minute. I'll load the file for the next demonstration. Okay. I'm just. So I just loaded the case file and data file in the Fluent Meshing. So this is a quad that we are looking for. So the setup meshings all are almost same what have been done to the previous problem. But here the problem is that we need to give some more extra input to the solver. So there are 4 propellers. So we need to give what's the RPM of this propeller. And also the catch over here is we need to must know what is the origin of this propeller. So maybe from what axis it is. So let's take this is in a center. From here, how much distance it's away from the center. So that we need to be aware of it. So that will help us to give you the axis of this whole propeller and also the RPM of this propeller is an input. So I just opened this solver in the GPU. I'll just tell you how to open it in the GPU. Just go to just type Fluent. Once you type Fluent in there, you can see a launcher window will be there. So in the solution mode, make sure it's in the enterprise. If it is in a premium, you can't activate the native CPU. It must be in the enterprise mode. Only the enterprise mode you can see the GPU can be activated. But in the premium, you can see it's dull. You can't check in, right? So make sure it is in enterprise mode. Once it's enterprise mode, you can see native GPU. And once you click native GPU, it will activate and it will print your GPU over here. And I want to, so you can see the it's printed, right? So I have a T2550 GPU with a 4.2 GPU with 16 SIMs. So this was a GPU that I'm going to have my hardware as that will be printed and you can start launching it. Okay, so I already launched it, so I'm just canceling it. Once you launched it, you can go to File and read a mesh, or maybe a case you have probably if you've done a mesh, you got to read a mesh and you can load it. It will load like this. But one of the most important catches or GPU doesn't allow you to do all the options which has been available in the CPU mode. So GPU mode has some limitation maybe on the, I can say, on the turbulence modeling where it doesn't allows all turbulence modeling, it doesn't have all methods. Yes, true that. But what my thing is, it allows you to do a drone simulation. For external aerodynamics, you have all the facility to be doing in GPU. So since you're focusing on the external aerodynamics, maybe for a quadcopter or maybe on the fixed wing, you can do a simulation. So you can for example, I'm opening a discuss model. We in this you can see a lot of turbulence modeling is been available, but here only few is available. Yeah, as I mentioned, K omega 60 is something best to go with. So I'm just going with the 60 K omega. Hello. Okay. And I'm just clicking a transient model because here, since it's a quadcopter, I just want to understand the vorticity on this quadcopter. So I want to understand that. It's transient problems. That's why I'm just closing the transient. You can see density based is not available in the GPU mode, only pressure based, which is enough for us. You can check the solver and you have to do the quality check and just move to the physics. And the physics I mentioned SST omega, and it's all same. I mean, I need to make sure the hair is the model. Okay, is the model of the fluid, and that's been mentioned. And make sure what is the you're flying from the ground, or you want to do what's in from the high altitude. So based on that, you make sure the operation condition and the material boundary conditions are being treated. And the important catch is the cell zone. So rotor 1, which has been a circular a dia will be there, which is being used to modeled as a MRF zone. So maybe I'll just show you one particular zone. In one particular zone. Let's take R1, R3, or C. Okay, so I'll just check in one particular zone alone to show a demo for you. So I created a enclosure. You can see I created an enclosure on this particular propeller that was being visible. So you can create the same enclosure in all this 4 propeller, and you can understand what is going to happen, what's the thing is going to be there over here. Okay, so that just enclosure is there. So that's how I need to give a MRF zone, as I mentioned. So I'm just stopping here and overhead it. I need to feed the two important data over here. What's the material need to be had, which is there, and make sure you're making a mesh motion. Make sure you have to make a mesh motion, and you need to do what is the distance. I mean, what is the away? I mean, how away uh, the origin of this axis rotated. So I know it's 0, 0,0.3 the rotor 1, and I want to know the axis and y-axis. I know the RPM, so 1200 RPM. And you know, right, two will be in a clockwise, another two will be in anti-clockwise. If it is an anti-clockwise propeller location, make it a negative. For a clockwise, make it positive. And same way, I'm just feeding it to all four rotors. You can see motion, and also I'm just feeding the origin and also the axis, and also it's a positive because it's clockwise. Same another rotor. Same thing, I'm just doing it for this also, and also the origin. Make sure it's in a mesh motion. And same over here. Axis, the exact location of this propeller, with x, y, z, and also the velar RPM and the rotational axis. So I'll stop here. Let me know if you have any question. I can address any questions here. I hope you're clear how to feed the RPM, which is very important on the quadcopters. Any questions? Yeah.
Are there conditions for meshing that MRF for propellers, sir? If
Okay.
possible, can you show that meshing for any one propeller with the moving frame?
Sure, I'll do that, ma'am. That is loading. I'm just loading that mesh also. Maybe once I'll explain the solver setup, then I'll show you the meshing. Meshing is loading. Just allow me some time. I'll definitely show the mesh.
Okay,
Okay.
thank you, sir.
Sure. Any other question? Fine. I'm just going next now. So once it's done, we have to look for the boundary conditions. So here, the propeller, there is no, only the outer thing need to be checked. So I'll just looking for that outer. It's a pressure outlet, which is the complete outer region of this propeller. Sorry, this complete drone. Maybe I'll just show you in the display. In the general display, yeah, it's there. It's this outlet. So here I've been choose a spherical domain. So I shown right in the during my space climb, I can select the cylindrical box and also a spherical. Here I've been choosing a spherical domain. You can see the spherical domain has been chosen. So that's why it's showing around this complete spherical domain it's named as a pressure outlet. So the boundary you can see it's named as a pressure outlet. I'm just giving a gauge pressure as an L0. Okay, so once it's all done, as I mentioned, you can just go to initialize, and you have to give a time step, a number of time step size, a number of time step, how much time that you like to solve, how much period like to solve, and you can hit the calculations. I have already calculated. I just kept it ready because it takes a lot of time, so I just kept it ready. I'll just load you the residuals for you. You can see the complete residuals over here. Okay. Maybe this the complete residuals that you look for. You can also plot the how much lift is there, how much drag you like to what. You can also plot all this also. But I like to show contours first. So let me show the contours and the velocity magnitude. I just kept it ready. It's loading. So until that, maybe loading. Just allow us some time. Okay, until this load, I can show you the mesh. Since there's a question on how the mesh is being done, this is the mesh that I've been done. Just showing in a, maybe I'll show you in the other direction. Okay, it's loading. Okay, it's done now. Let's allow some time. So you can see, right, import, I done a local sizing is also done. So local sizing has been done separately for all the propellers. Let's go closer. Maybe I'll just undraw the mesh layers. That allows you to allow some time. That's loading. So I need some time. It's loading, both is loading. So let's allow whatever comes first. Okay, it comes fast. It's loading. Let it load. It's loading. So let's allow some time for both to process it. So until that, maybe I will discuss some, I just like to answer your questions, or else we can, I can I just continue my presentation with a best practice until it loads. Let's have some, I'll just continue my presentation. But before that, I'd just like to know if you have any questions. So can I answer any of your questions?
Sir, I have a question. How can we decide that only and steps are required for how many? Is it dependent on how many rotations the propeller should complete, or
Sorry, actually, I couldn't hear your question. Can you please come again? There's a lot of disturbance. Can you please come again? Others can also drop it in the chat. Better.
Okay, now am I audible, sir?
You're better. Please go ahead.
Yes. Actually, I was asking that how many time steps are needed for like a reliable solution, or what like number of rotations decide, or what should be the criteria for selecting number of time steps for transient analysis?
Okay, it depends on the how much time you want to do it. At least, for example, I like to know the vorticity, right? So if I want to know the vorticity, I know the RPM, how many minutes, for example, for a minute, it rotates for 1,200 RPM. So now how much time I want to see the complete vorticity, I need to decide. So I just need it for 30 seconds. I need to set up the time step and size according to that. Maybe over here, I done it for 0.001 into 260. Just multiply those. How much second it is? Come on. It's, hello, are you there? It's 0.26, right? Hello. Hey, am I audible?
Yes, sir. Yes, sir. Yes,
Yeah.
sir. Yes.
So that decides it. So how much second steps is depends on the how much time of period that you like to solve. So you can see right the verticity in the my screen. So I know the RPM. So in that second, how much rotation it will be. So that at least I need a one particular rotation. That helps me to understand the flow. It purely depends on the RPM of the propeller and how much times it's how much second you like to visualize the verticity. So you can see the verticity in my screen, right? Okay. So that's this how we can understand the verticity, and this allows us to model it your drone lesser sound. Yes, truly it's possible, and also you can plate generate a force. How much force is being generated? You can also go under the force, and I just also created some scenes. Maybe I'll just show you the scenes. So I just the quantum magnitude and also different scenes also you can create, and you can understand, you can see, I mean, I just do the velocity on particular plane. So you can see a velocity on a particular plane. What's the airflow velocity on the propeller because of this propeller. So you can create a plane across any condition and you can look into it. Okay. I hope you answered your question. You have anything to discuss? That is fine. You got it right?
Yes, sir.
Okay, thank you so much.
It is fine.
Okay. And also, if you want, I can also see the, wait, I'll just say, I also want to see a verticity. What vector? Yes, that is also possible. I just already created the vector. You can see the vector flow on the plane because of the propeller, how the, how the vertex is being formed on the propeller. So maybe by changing the propeller length, changing the pitch angle of the propeller, or maybe increasing the distance of the arms, you can understand how the aerodynamics of the quadcopter is getting affected. And with RPM, by changing the RPM too. So these are all the factors that we will change and parameterize it, and we'll understand the aerodynamics of the quadcopter. And on the meshing side, it's better now. Maybe I'll just load it. I want to see the, sorry, it takes some time, I guess. Let it load first. Okay, I need to allow this. I'll just allow this. Maybe I'll just let it take some time. Then I'll just show you the meshing side of this propeller also. So any other further questions? So do you have any further questions you want me to answer? I'll just select the chat also. Okay, any questions on the chat? Feel free to even drop your questions on the chat. Okay, I'll just go to some best practices ideas. Then maybe at the end, I'll show you the how we can discuss on the mesh side. It's done, I guess. Maybe let me try. It's still rotating. And so actually, I didn't have actual fine measures to capture the verticity to show you the verticity, but it's takes some time. Maybe until it loads, I will maybe I'll just explain you the best practices. It takes some time, so let me allow some time on that. Okay. So external aerodynamics measure, we look for the forces acts on it, aerodynamic forces lift and drag on the different configuration like geometry, different shape, different angle of attack, while taking a payload, without payload. So we'll understand how the geometry is affecting the aerodynamics. And the meshing perspective, we must understand the surface mesh distribution, growth rate, and yes, and the local sizing matters a lot. You must work on that. And also the meshing grid independence study matters. Maybe in the upcoming slide, I'll explain you. And also always recommend the right domain size based on your blockage ratio, 3 to 5% somewhere. You just plan your right adequate domain, and inlet and outlet boundary conditions always recommended. and also discretization schemes. You're using simple, simplic, or coupled. It's purely in the, if it's a transient, I recommend you to go with coupled. For steady, simple and simplex works much better. And also flow conditions like angle of attack, Mach number, and also velocities, all this affects. So we have to make sure, maybe if angle of attack is higher, if you're expecting a huge force operation, make sure you're using a right turbulence model. And also, when it comes to the Mach number, if it's in a high, its compressibility effects is there. Make sure you're choosing a right turbulence model, also the right setup. So these are all the factors which are being meant to be focused when it comes to a best practice. And mesh resolutions also matters a lot. So when it's a coarse mesh, you can see coarse, fine, and medium and fine mesh, the CD values keep on affecting. We should keep on meshing and checking your answer. With respect to irrespect to the fine mesh, when it comes to when you get a stagnated result, that point is considered to be a right mesh sizing. So you have to do a grid independency study to make sure the adequate mesh sizing is being done. So that is an extremely important factor. And also make sure you are giving a right mesh number of mesh layers, boundary layers on the surface, somewhere between 10 to 20 to capture the boundary layer effects. And also the best practices on the geometry and flow parameter, I also mentioned the angle of attack thing. So make sure you are converting the normal force as well as the axial force into respective drag forces and the lift forces. That's very important. And make sure you're also respecting a CL-CD ratio according to your, so CL and CD can be solvable, but ratios that we need to calculate that need to be taken care from our side. And only the aerodynamic forces will be obtained from the solver. So you have to balance your right calculation on the weight to lift ratio and thrust to drag ratio. And the robustness, it's always robust when we have one inlet and one outlet. So make sure you're using a velocity inlet or pressure outlet. Yes, you can use fast flow rate as also as a boundary condition, and yeah, total pressure, but it's all sensitive. But my complete recommendation is always use a velocity inlet or pressure outlet. That's something in the quadcopter, use only the pressure outlet. And if required, you can keep the velocity and pressure on the outlet in the top. Depends on your requirement, but don't go like a static pressure inlet, as a total pressure inlet, or mass flow rate as an inlet. That seems to be a little tricky, and since insensible and not robust enough to solve the problem. You can try. I hope most of you are on working on the incompressible low speed subsonic flow. The pressure-based coupled solver is somewhat better to go with, but you can also think about density-based when it comes to high-speed aerodynamics or highly compressible flow for your problem. Okay, so if you have any questions, please feel free. I mean, if you want to if you're working on a tailored project or you want to ask me any questions, feel free to ask. Have any questions, guys? Sure.
Sir, from the solution, can we also get the total thrust generated by the multirotor?
Yeah. Yes, ma'am. Trust the force, right, ma'am? So we can consider yes, that is possible. Even each and every particular propeller also is possible to get it. And also it's possible to get a complete body also. You have to select the unmanned aerial vehicle, I mean, that complete body, and you have to give a right axis and just generate, click force. It will give you the force. It's possible.
Okay.
If it's an aerodynamic thrust, yes, it's possible to do that.
Also, sir, while doing the setup, you have given a pressure outlet to the external face of spherical that bound domain. So, is there any inlet face or only outlet face you have given?
No, only pressure outlet is given. There is no inlet. The flow is happening completely due to the rotation of propeller.
Okay, sir. And is there any in CAD? Is there any connection between the propeller and the rest of the body of UAV?
Yes, that need to be right. I mean, the connection will be there, but surrounded by the propeller, we will need to have a. We need a MRF zone. That's it. The connection is required.
Yes. So you are saying that the motor shaft should be there.
Yeah, shaft need to be there. Yes, but we don't need the exact feature of it. Just a connection need to be there. Then only it will consider as a complete one body. The body should not be separated. For example, a propeller and a airframe should not be separated. It must be have a connection. If it doesn't have a connection, both will be considered as a two separate body.
Okay, sir. Okay. So the connection can travel through different domains, right? The MRF, whatever domain that we created for the
That
propeller.
is domain. I am that is domain, but you must have a propeller need to be connected to the shaft. Then only the complete drone will as a single body. Maybe I'll just have one particular propeller. So what you see in my screen is a quadcopter, right? This is a quadcopter. So what you can see is a complete solid. It's a complete solid. When it comes to a complete solid means when it has no disconnection. It should not have any disconnection. You can see, right? It's been connected.
Yes.
Okay.
Yes,
But you can make sure you can have a motor as only spherical. Spherical zone. You need not have a right feature of the motor. That is fine, but you should have. It need to be have a connection. Okay, you can opt. You can assume it as a complete perfect cylinder. That is fine, but it should have a connection. It should not be have any disconnection.
Okay, sir. And can you please also show the MRF domain, like how it is created? So
let's create. You can see the enclosure, right?
Yes, sir.
You can see this enclosure on the left hand side. So once I set an enclosure, I have created an enclosure. Maybe I can just create an enclosure by selecting the particular drone. Maybe I'll just go here. I can select it, clicking. I have selected the complete propeller, right? This propeller has been selected. I'm just giving a demo. It's already created. I created the MRF, created the zone. You can go to design it, just go to prepare, and you can create enclosure again. It's I to just give me a second. Put in the right place. It's now we can create it in this way. Okay, we can also make a circle on this. This is also a way to create it. So we can take the center. This body is completely attached, so I need to disable this propeller out of it, and also I can create, but I just doing it this way. I just made a circle, and you can click a pull option and no merge option, and there we go. And you can this way you can click a more of zones. Once you're done, you can I made a approximate circle cube out of it, but you can do it in this way. So once it's done, you can also use a combine option to feed this out of this feed this propeller out of it. So once it's done, it will be separated separately. Okay. This is the way we can create the MRF zones. The one way. And also the another way is you can keep make this propeller separate, and you can select only this propeller and make an enclosure. That is also possible. There are two ways to do that.
Okay, sir. Thank you.
Okay. Okay. So I've just created the 4 MRF zones. Okay. And one particular here I used enclosure, not a spherical, but a cuboidal enclosure. It depends on your requirement. You can use any kinds of enclosure based on your requirement. So any questions? Any further questions? So kindly share your feedback, just scanning this QR code. So you will have a feedback form. You can please feel free to share your feedback. And also the same feedback forms link is also available in the chat. And maybe I'll just copy and paste it again now. Feel free to share your feedbacks about the program. So that will help us to do mesh better and better in the future. So if you have any questions or any specific questions, I'd like to address. If not, I'll just move to the final part of the program. Any questions?
Sir, can we get the recording of the session?
Yeah, so we are recording it. Yes, we will get it. Definitely.
And if you are having any problem while we are doing analysis, is there any way to contact you or get help from Ansys?
Yeah, you can always, if you have any questions, you can drop it in the Ansys Innovation post. There are community, they will help you to understand. So I'll just maybe in Ansys Innovation post is there. From here, you can go to support and you can ask for any questions, general questions. Frankly, you can ask. They will help you to address that. And also, I'll just give you this workbook with you. So this has fundamental contents. This complete contents from CAD lab. This will help you to do how to do a modeling in using a space client. And this will help you to understand the fundamentals of the computational fluid dynamics from geometry, meshing, setup, customization, solution, post-processing. If you just click the link, it will take you to the course. You can start learning it. And also, we have a dedicated some different problems. So you can use this to learn the different application perspective problems also. And I have it for a finite element method also, FEA. I will share this with you all. And also, in addition to that, maybe I'll just recommend you to go across this particular courses. So these courses will help you to understand. If I just click go to course, it's a GPU. It's as how to use a drone. So you can use a generic drone. So you can see a course two is that's Fluent GPU using a feature of drones. So you can learn it from here also. So you can write to support, and also I give you this PDF, which I'll take you to the respective Ansys innovation course, and also I'll share some external aerodynamics as well as drone related courses. I mean, that will help you to course around the Fluent solver. I will share all this with you to the organizer. Organizer will share with you all. Okay, maybe I'll just sharing some links in the chat. You can also start the learning as soon as possible. So, any questions? I shared a solid modeling of a drone. Sorry, I shared the also the GPU of the drone. If you want any, and also the PDF, I will share that with your organizer. Organizer will share with you. So if you have any questions, feel free to. I'm happy to answer. Okay, assume there is no question. So there. Yes, Mr. Vikas, please let me know what's your question. Oh, sure, definitely. We are happy to be there. Please stay in touch with your organizer. We'll do, and also please follow our CAD from India LinkedIn page and Ansys LinkedIn page. You will be notified with a lot of webinars and training programs. So feel free to follow us in Instagram, YouTube, LinkedIn. So you will also notified with a lot of webinars like this. Okay, thank you so much. Welcome, Mr. Vikas. So I have shared some contents in the chat box. You please go across these contents and also kindly fill the feedback form. That will help us to do more sections like this. We'll feel happy to hear your feedbacks. Sure, I will share all this with the organizers. Organizers will share with you. Okay. Thank you. So there is no questions. We can drop off.
Sir, what about the meshing of the reference frame, sir?
That is same, ma'am. I'll show you. Okay, let me show the references frame is, yeah, it's loaded. I can show you that. Just give me a second. You can see my screen, ma'am.
Yes, sir. Yes, sir.
So this file will be there in the link that I shared with you. So you can take the mesh file and also have a see. It's something that you need to do a MRF only on the MRF particular MRF zone. You need to do a fine mesh. Okay, so you can see a face sizing, right? You can face size the MRF zone, and you can do a meshing. And also you have during a volume mesh also you can do a fine mesh inside the MRF zone. It purely depends on your requirement. If you don't need it, you can do it. Okay, you need to do a meshing also. Okay, any questions?
So around that propeller, including the propeller, should be fine mesh area.
Yes, because we have to capture the physics around that, right? That's why.
Okay, thank you.
Okay. So any question? Let me check the chat box. Yeah, so current section will be the organizers will share with you. Definitely will share them. Okay. So any questions? Any further questions?
Sir, actually, we are running these transient analysis on our laptop. So can we do a trade-off between the element size, minimum element size, and the results that we have to get from like vorticity and trust data? So
Yes,
is there
for
any way
example,
to increase the
yeah, I will recommend to do a grid independence study, as I discussed. You do, for example, let's take you have done a simulation of 2 million, then do it for 2.5, then 3, 3.5, 4. So what happens is you need to look for the result. Let's imagine I'm just looking for a lift or a thrust force acts on the quadcopter. Maybe for 2 million, I got 20 Newton. 2.5, I got 25 Newton. 3, I got 25.6. So I can stop with 3, right? So the difference is extremely negligible. But just even go 0.5 million extra. So that's how you have to fine tune your mesh. That's how we need to do a trade-off.
Okay, so
So grid
we have
independence
to
is very
manually converge the solution.
Yes, we have to check manually if you increase the mesh size, is there any change in the results or not? If there is no change, you have to stop just one step behind that.
Okay, sir. Okay. Thank you.
Thank you. Any further questions? Okay, if there is no question, so we can close this today's meeting. So kindly fill the feedback forms, and also please I'll share this PDF, learning content PDF, and also AIC courses links in an email with the organizer. And also, I recommend you all also to please look at the Ansys Innovation course, and please get benefited out of it. Thank you so much. Oh, there is a question. Yes, Shimnaya. Yeah, you can unmute yourself or maybe type your question. I'm happy to answer. Shimnaya, please go ahead.
Can you hear me, sir?
Yes.
Actually, we were told that there was also going to be a talk on aero acoustics.
Okay. Yeah. This is what I've shown the Vorticity, right? So this Vorticity decides the how the acoustics level is going to. I mean, how your acoustic level of your study is going to be. This because they are this the acousticity is just purely due to the pressure difference. Maybe I'll just share my screen. So I hope you are there while I'm showing the Vorticity. I just save this place. Just give me a second. It's loading. And also what you can measure the decimal level. Just allow me some time. You can see the physics acoustics, right? So in the acoustics, in the latest versions, you can do acoustic study in a GPU mode also. So in acoustic, you can go and select the acoustic model, and you can just need to give two inputs. One is source and the receiver. Source is the drone over here. So from which propeller you would like to, maybe let's take only one particular propeller, or maybe a group of propeller that became a source. And from there, how it's a receiver, how does the distance between the source and the receiver that you need to feed it. And once you feed, you will get the decimal level. And also you can get the graph out of the what's the hertz with respect to the time. That can be predicted on there. So the major part is you need to understand whether the design is on the vorticity, how much the vorticity is there, how much the sound is going to be.
Right. So for that, I have actually done a simulation of aeroacoustics in Ansys. So we just wanted to know like how to extract information from there so that we can actually use it in our to build a drone basically.
Okay, extract information in the sense what kind of information you think about?
Yeah, so I did the fast Fourier transform and I got like the sound pressure level. So it was showing decibels and frequency. So that will be directly used as like the noise that is being produced.
Yes. Yes, that is because sound is measured with the decimal, right? That has been directly used.
Okay. Okay, sir.
Okay. Thank you. Now, from there, I mean, how you decide it? Now, for example, you're getting let's take a 220 decimal in the receiver point. Now you can also change the pitch level, or you can increase the shape in the hub on the propeller, or respect to you can change the RPM of the propeller, and you can do the design trade with your acoustic in this way. I hope you answered. Okay. Thank you. Okay, there was another question. Can you please provide a link in a sequence which will be, I'll share the PDF. In that PDF, it will be our fundamentals of complete computational fluid dynamics and find the element method. It will be on the sequence. So from there, you can just start learning it. Maybe from the tool perspective, like space climb, discovery, and also Fluent, it will be in the sequence. You can refer my PDF that I provide, and from there, you can definitely start learning. Yes. So any further question?
Sir, I had one more question. Sir,
Yes,
why
ma'am.
is it advised that for a CFD analysis, the model should be a single solid body and it should not contain any surface bodies or surfaces?
Because we need a clean body, ma'am. Without a clean body, it will be difficult for you to have a mesh, right? That's the first thing. Okay. If you have a multiple small surfaces pictures during meshing at that particular surface, it will lead you to do a fine mesh, which will increase your computational expense. And also there is a chance of mesh failure. So the disconnectivity will never develop a mesh. And as you mentioned, there can be a multiple CAD, but it need to be connected. If it is disconnected, you can't develop a mesh across it, right?
Yeah, okay.
It's purely because for the getting good mesh, we are doing this.
Okay, thank you.
Okay, in the drones, what I've shown, maybe if you take, you can look near the propeller, where the motors, everything will be a perfect cylinder. But in general, motor is not a perfect cylinder, right? But we'll assume it as a perfect cylinder. We'll do some cleanup across it, and that is required in the especially for CFD simulation to avoid this kind of unwanted meshing operations. That's it.
Okay, sir, in this moving reference frame method, the propeller and drone is actually attached, but we are keeping it as two separate bodies.
Yeah, MRF there need to be 4 MRF and 1 drone need to be there, and apart from that, 1 enclosure need to be there. There are need of 5 bodies. 1 body is a drone, 4 MRF different bodies, and 1 complete envelope.
Okay, okay, sir.
So any further questions? Ladies and gentlemen, any questions? Okay. If there is no question, we'll close this call. Thank you so much for attending. I appreciate all of you for being a part of this workshop. I wish you all the best for your future endurance. Please follow us on the LinkedIn, CAD India, as well as Ansys. So you will be informed a lot of certain webinars and workshops. It's been happening across, and feel free. Thank you so much, everyone. Thanks a lot. And kindly fill the form also. Feedback form.
Thank you, Mr. Vignesh. Thank you so much.
Thank you so much, Mr. Vignesh. Thanks a lot. Mr. Dinesh, are you there?
Yes, Vignesh, please.
Dinesh, I will just share some learning PDF as well as some AIC links with you. Kindly share to all the attendees.
Yes, definitely.
I will just inform Venkat to share with you. So please kindly share all this with them.
Please. Thank you so much. Yeah.
Okay. Thank you so much, Dinesh. Thanks a lot. Okay, I'm closing the call. Thank you, everyone. Wish you all good luck.